In the first video of this series, we discussed some basic elements of colour science. Today, we're going to turn to the philosophy of colour. And the central question for us is, what exactly is colour? When we look at the world, it certainly seems as though objects have colours. It seems as though colours are straightforward properties of objects. Grass is green, a banana is yellow. Yellowness is a property of the banana, like its mass or starch content. Well, I hope that one of the things you will have learned from the first video is that things aren't as simple as that. So there's quite a lot of room for philosophical debate here. Now, there are essentially three families of views. First of all, realism. According to colour realism, objects have colours objectively. Colour is the property of colour is independent of the human mind. It exists, in the external world objectively, and a significant portion of our colour perceptions are veridical. So when we say grass is green, this is true. It's true because grass has the property of greenness. And it would have this property even if no humans or other sentient animals had ever been around to see it. So there are essentially two types of realism, reductionism and primitivism. According to the reductionist, colour can be identified with some standard physical property. The view that colours are wavelengths of light is a reductionist view. Wavelengths of light are physical properties. We'll be discussing reductionism in detail in this video. Primitivism holds that colours are irreducible properties. Colours exist in the external world, but we can't identify them with some other property. Colours just are exactly how they appear. They exist in some sense over and above the physical properties. That might seem a bit confusing, but we'll look at that more closely in the next video. Second, anti-realism. Anti-realism is the claim that colours do not exist in the external world. Nothing out there is coloured. So immediately the vast majority of our colour judgments are going to be wrong. Grass is not green. Bananas are not actually yellow. So one option is to say that colours are properties of the mind. They're perhaps properties of sense data or something like that, which we project onto the world. More strongly, we might hold that colours simply don't exist at all. Colour is just a massive illusion. And this is colour eliminativism. It may be worth noting that anti-realism is probably the most popular view among colour scientists. When you hear scientists talk about colour, they will often say either that colours don't exist or that colours are just subjective properties of the mind. They're not properties of objects. Third, relationism. Relationism tries to find a middle path between realism and anti-realism. Basically, the claim is that colours are real properties and they're not just products of the mind, but also that they can't be defined completely independently of observers. So the simplest version of relationism is dispositionalism, according to which colours are dispositions to cause certain kinds of experiences. Something is red just in case it looks red, or causes a distinctively reddish sort of experience in normal observers in normal conditions. So a standard comparison here is to something like poisons. Something is a poison just in case it tends to cause illness when ingested. Poisonousness is a relational property. It's a matter of how a particular substance interacts with an organism. So it depends on that relational interaction between the organism and the substance. Okay, so those are the broad options. I suppose I should note that my own inclination is pretty much towards eliminativism. I'm tempted to say that colours don't exist. I'm not completely convinced about that, but that seems to me the most attractive theory, so that's where the biases in this series will be coming from. But I'll do my best to present the other views fairly. So we're going to start off with realism, specifically reductionism. I think reductionism is initially probably the most sort of obvious theory of the lot of them. As a form of colour realism, it's in line with common sense, because colour does indeed seem to be a mind-independent property. Objects appear to us as though they are coloured, and it looks as though we can be right or wrong about colour. Grass is green, not red. If somebody says grass is red, they're just wrong. If they said it's green, they're correct. And an important point here is that changes in colour track real changes in objects. If I dunk my hand in hot water, it will go red. If I have a mole that starts changing colour, or I notice that my legs have gone blue, that tells me I need to see a doctor. And we can exploit colours in various sorts of ways, as when animals use colours to camouflage themselves from predators. So initially, realism seems like the kind of initial position. Reductionism, specifically, is very much in line with the naturalistic, scientific approach that most philosophers these days favour. There's nothing spooky or supernatural about colour. It's a standard physical property. It's just like mass or charge or whatever. So certainly this reductionist brand of realism is an initially attractive position. Okay, so a simple form of reductionism is to say that colours are wavelengths of light. You maybe sometimes hear scientists say this. They'll say redness is just light waves in the longer wavelengths of the visible spectrum. I don't think this is very popular among philosophers. There are many problems, but the central difficulty here is colour constancy, which we discussed in the last video. You can classify objects as having the same colours even under significant changes in illumination. It's a central feature of our visual system that colours are mostly preserved under different illuminants. The colours you see under daylight are basically the same as the colours you see under tungsten light. There'll be some differences, but they're at least very, very similar. But the wavelengths reaching your eyes are very different. So colour constancy suggests that colours are illumination independent. Assuming that colours are mind-independent properties, they are presumably properties that attach to objects and don't change as the illumination changes. Our visual system is able to track these properties, and they remain stable even as the illumination changes. So the wavelengths reaching our eyes are going to be very different when you look at an object under daylight and when you look at an object under tungsten light, but the object will probably look to have the same colour. So it's difficult to identify colours with wavelengths of light. I should also notice that an odd consequence of this form of reductionism is that actually most colour statements are false. So it's not obvious that this is a form of realism at all. If I say, for instance, grass is green, well, actually that's false, because grass isn't the kind of thing that can have colour. To say that grass is green is really just a category error. Grass reflects green light into our eyes. It's the light that's green, not the grass. Similarly, this view entails that when the lights are switched off, it's not just that you can't see the colours anymore, the colours literally disappear. So again, that's rather odd, and it's not clear to me that that's really a kind of realism, because realism would entail that most colour judgments are true. But as I said, I mean, the main problem with this view is, I think, colour constancy. So perhaps a more plausible version of reductionism is proposed by Alex Byrne and David Hilbert in their article Colour Realism and Colour Science. It's kind of a technical article, but it's very good, and it's freely available on the internet, so you could go and read that if you want. They suggest that we identify colours with surface spectral reflectances. The spectral reflectance of a surface is the proportion of light reflected as a function of the wavelength of incident light. So we can graph surface spectral reflectances like this. This shows a variety of spectral reflectances. So this line here, this sort of darker grey line, is a lemon. And you can see that it reflects very little light in the short wavelengths, as we would expect, because those shorter wavelengths are associated with blue. Quite a lot of light in the medium and long wavelengths. You recall from the last video that the medium and long wavelength cones combine their input to make the yellow channel. So that kind of makes sense. That's what you'd expect from a lemon. Lemons are yellow, and you can see that here. This slightly lighter grey line is a marigold or an orange. As you can see, that's shifted to the longer wavelengths, as you'd expect, because oranges and marigolds are redder than lemons. So that's fairly simple. Now, unquestionably, surface spectral reflectances are properties of objects. They are objective. They're mind independent. And furthermore, they're compatible with colour constancy. If you take a lemon and put it under different illuminants, it will reflect different wavelengths, but its surface spectral reflectance remains the same because the spectral reflectance is defined for all wavelengths. So this is sort of what the kind of property that we're looking for. We wanted something that is compatible with colour constancy, with the way that colours remain the same under different illuminants, and surface spectral reflectances provide just that. Recall also that one of the points we made in the first video was that two things can have very different colours despite significant physical similarities. Emeralds and rubies were the example I gave. Well, spectral reflectances provide a neat solution, because if two objects have different colours under the same illumination, they must have different spectral reflectances. So this is the physical difference that explains why two seemingly similar objects appear differently coloured, right? Why two objects which have the same, or at least very similar physical structures, will appear to have totally different colours. It's because their spectral reflectances are totally different. So that's the physical difference that explains that. Now obviously spectral reflectances are only half the story. As we saw in the first video, colour arises through a variety of processes. But we can generalise the theory. We can talk about surface spectral productances, and this is the proportion of light reflected or transmitted or emitted as a function of the wavelength of incident light. So the spectral surface productance is basically just a matter of the light coming off the object, however it may have interacted with the object, as a function of the wavelength of incident light. I'll continue to talk about reflectances because it's easier and simpler, but keep in mind that the theory can and must be generalised. So Byrne and Hilbert's proposal is that colours are surface spectral productances, and for the standard opaque objects that's going to be surface spectral reflectance. Okay, so that's the basic theory. Let's turn to some problems. Well, a significant challenge to reductionism is posed by metamerism. We mentioned metamerism briefly in the last video. Our three types of cones make for a very coarse colour detection system. Two types of light of very different physical composition can produce the same response. So we say that coloured lights are metamers if they are perceptually indistinguishable but differ in their spectral composition. For instance, pure 577 nanometer light will appear yellow. Light that's 50% 540 nanometers and 50% 670 nanometers will be totally indistinguishable. It will appear the same yellow. Similarly, reflective objects are metamers if they match under a given illuminant but differ in their spectral reflectances. And the differences can be significant. Here's a graph, 4 graphs showing 4 spectral reflectance curves that are indistinguishable under daylight. These all appear to be yellow under daylight. Very, very different. So some metamers match under a very wide range of illuminants, but they can differ significantly in their spectral profiles. So the question is, how exactly can we identify colours with spectral reflectances if the same colour can have completely different spectral reflectances? So one initial option is simply to hold that metamers are in fact different colours. Colours are spectral reflectances. Two indistinguishable yellows have totally different reflectances, so those two yellows are in fact different colours. Bear in mind that if we accept colour realism, if we accept that colours are mind-independent properties, it really shouldn't be surprising that we're not able to distinguish colours perfectly. No perceptual system is perfect. Indeed, in general, note that some people seem to have better colour discrimination than others. Two people will fail to see the differences between hues of hues of the same colour that others can clearly distinguish. You know, one person will look at two different hues of the same colour and be unable to distinguish them, whereas somebody else will look at them and easily distinguish them. Similarly, people have different abilities to distinguish slightly different levels of saturation. So we often call two colours yellow while still recognising that they're actually different. Now, one of the worries about this response is that it's not simply a question of failing to discriminate closely related colours. You might look at two yellows and fail to see any difference between them because they're so similar. That's no problem, because we can specify what unites them, namely they're both yellow. The problem of metamerism is that two indistinguishable yellows could have totally different surface spectral reflectances. So if colour just is surface spectral reflectance, we have to say that these two yellows are in fact totally different colours. It's not simply that they're different shades of the same colour, like mid-yellow and a slightly darker yellow. It's rather like the difference between yellow and purple. And so then the question is, what does this view have to do with the colours that we believe in? There's a worry that this is really just a kind of disguised anti-realism, because on this view, most of our beliefs about colours, most of our perceptions about colours are wrong, or at least radically incomplete. So this, I think, a lot of people are going to want to resist going down this kind of route. A second option, the one favoured by Byrne and Hilbert, is disjunctivism. So this is the idea that colours are to be identified with disjunctive sets of spectral reflectances. We say that, for instance, red is property A, or property B, or property C, or property D, etc. And then we fill out that list with by listing all the spectral reflectances that appear red to us. So groups of spectral reflectances are determined by their effect on the visual system. Bear in mind that we would have to say this anyway, because there are many reds, right? Some reds are more yellowish, some are more bluish. So we would have to group spectral reflectances together like this anyway. Of course, the initial hope might have been that these reflectances would at least all be similar. So all the red reflectances are similar, and all the green reflectances are similar, and so on. Metamerism forces us to create very odd collections of reflectances. Recall the metamers for yellow that we saw in the last slide, right? So they don't appear initially to have anything to do with each other. So we have to create disjunctive sets. It's A or B or C or etc. Byrne and Hilbert call this anthropocentric realism. It's anthropocentric because the reduction is carried out with respect to the reactions of human perceivers. That's how we determine the sets of reflectances. Nevertheless, it's still a form of realism because the reducing properties are still mind-independent properties. If we take some set of spectral reflectances and they all look red to us, well, this set is completely uninteresting from the point of view of physics. In purely physical terms, it's just an arbitrary collection. But that doesn't mean it's not real. That doesn't mean it's not mind-independent, just because it's arbitrary. Redness is this set of reflectances. Redness is the set of reflectances that appear red to us. Anything that has one of those reflectances is red. And that's a mind-independent property, because the reflectances are mind-independent. So although we have to consider the reactions of human perceivers in order to specify the set of reflectances, the reflectances themselves are mind-independent and objective. So this is still a form of realism. Or so Byrne and Hilbert say, but I can't help but feel there's something kind of weaselly about this kind of argument. So one objection is, well, look, the set of reflectances for each colour is just going to look completely gerrymandered and arbitrary. So it's true that for each reflectance taken individually, that reflectance is mind-independent. Okay, each individual reflectance is mind-independent and objective. But the only thing that unites them as a group is the effect they have on human perceivers. There is no mind-independent unifier. Metamerism means that the reduction, in scare quotes, the reduction of colour to physical properties can only be carried out by reference to the idiosyncratic mechanisms of human perception. So I guess one way to put this point is in terms of prediction, right? For some new physical property X, for some previously unseen spectral reflectance X, does X belong in the red disjunct or in the yellow disjunct? Well, the only way to answer that is to ask how it would affect human perceivers. So the worry here is that we're just giving up realism at this point. This is really a kind of dispositionalism or relationism. This is not a realism, because there's no way of specifying these sets of reflectances without appealing to the mechanisms of human colour perception. So anthropocentric realism threatens to collapse into some sort of relational view like dispositionalism. And this leads us neatly to a second objection. Even if anthropocentric realism doesn't ultimately collapse into dispositionalism, it still faces many of the same problems as dispositionalism. Now, I'll deal with these problems when I come to the video on relational views, but just to give a brief example here. Anthropocentric realism requires us to specify normal observers and normal conditions, because human colour perception is not just one thing. Different people, even different people who are considered to have perfectly good colour vision, will see colours differently. There's a wide range of variance in colour perception. For instance, what appears unique green to one observer may be identified as having a distinctly yellowish component by another observer. There are gender differences. Objects that women identify as a cream colour, men are more likely to identify as white. And of course, even a single individual will see colours differently in different contexts. So Byrne and Hilbert want to specify their disjunctive sets of spectral reflectances in terms of the effects on the human visual system. But those effects are going to be different for different people. As I said, I won't go into detail on this here, but you can see where Byrne and Hilbert are going to start to run into difficulties, because the question is going to be, well, how exactly do we specify what counts as a normal observer? How do we specify what counts as a normal condition? And that's very difficult. Again, I'll look at that in the video on dispositionalism, but when we get to that, just bear in mind that anthropocentric realism is going to face many of the same problems. A third objection is that anthropocentric realism can consider colour perception only as it pertains to humans. Presumably other species can see colours, so we would want our colour theory to apply to all species. But if colours are just disjunctive sets of reflectance profiles specified by the effects they have on the human visual system, it would seem to follow that species with different visual systems don't see colours, or at least they're massively mistaken about what colours are. In any case, we're certainly going to run into problems if we try to talk about different species seeing colours. In fact, this is a problem even for other humans. Many humans are colourblind. They are dichromats. But we assume that they still see some colours. Though obviously they can't identify the same sets of reflectances that normal people can. And this becomes particularly odd when you consider that there are some people who are dichromatic in one eye and trichromatic in the other. They certainly think that they can see colours using both eyes, but initially at least it seems that this theory entails that they don't see any colours at all through the dichromatic eye, but they do see colours through the trichromatic eye. So that's a bit of a problem. Now, one possible attempt to extend the theory to other species and to colourblind humans would be to define different sets of spectral reflectances as different colours beyond what normal humans can see. So each species sees different colours. Each species has a different collection of sets of spectral reflectances. For instance, dogs see the reflectances A, B, C and D as a colour. Humans see A and B as one colour and C and D as another. So A, B, C, D, that's one colour. AB is another colour, CD is another colour. Now notice that this means that the same reflectances can have different colours. Indeed, on this view, every object has an infinite number of colours. Reflectance B, for instance, is part of the set AB, it's part of the set ABCD, it's part of the set BFZ, it's part of the set BHJK, and so on. Now, it counts as red because it's part of the set that has the appropriate effects on the human visual system. So it counts as red because it's part of the set AB, say. But it's also part of infinitely many other sets, and hence it counts as infinitely many other colours, which seems a bit odd. It's a slightly bizarre result. I'll discuss this kind of view a little bit more in the next video, but immediately this looks rather odd. An interesting suggestion from Paul Churchland is that, in fact, there is an underlying physical property that unites the metamers into sets that correspond to the colours we see. This is discussed in Churchland's article on the reality and diversity of objective colours. Churchland points out that when we represent spectral reflectance profiles, we portray them as a straightforward two-dimensional graph with the colour spectrum moving from sort of violet to red. So like this, in other words, that's the normal way of representing spectral reflectance profiles. So we have the colour spectrum here, we have kind of violet. I don't know if you can see that, it hasn't come out so well in my photo, but it's sort of violet all the way to red. Now, notice that each end of the colour spectrum tends towards purple. Doesn't quite get there. Purple is a non-spectral colour. No single wavelength of light will appear purple, but if we were to kind of extend this naturally in each direction, we would fade into purple either way. After red comes purple, after violet we get purple. So here's an idea. Let's take this spectral reflectance graph, okay, and roll it into a cylinder, okay, because as you can see the spectrum here fades into purple either way, so that suggests we could join the ends, right? And we can do the same then with this graph. Okay, so we roll it into a cylinder and connect the 400 nanometer and 700 nanometer ends. And as you can see, here's Churchland's representation of this cylinder, right? So we take the graph, roll it into a cylinder. Now what we can do now is approximate the reflectance curve by making an imaginary cut through the cylinder, essentially a line of best fit, generating an ellipse. And this is shown here, okay? So we take this kind of line of best fit by making a cut through the cylinder, and that generates an ellipse inside the cylinder. This ellipse is an approximation of the spectral reflectance curve. Churchland calls this ellipse the canonical approximation of the spectral reflectance curve. Every spectral reflectance has a canonical approximation. Canonical approximations are objective features. We can specify these canonical approximations without making reference to the human visual system. As you can see, I've just done it there, right? We didn't have to talk about the human visual system in order to make this ellipse. So Churchland says these are just straightforward objective properties of spectral reflectance curves. Now these ellipses have three features. They have the altitude of the centre point. So the centre is, I guess, is somewhere around here. The altitude, how high that centre point is. Second, the tilt angle. So this is the degree to which the ellipse is tilted away from the horizontal. So the horizontal ellipse would just be straight on like that, whereas this is tilted quite high, so this is quite a kind of high tilt angle. Third, the rotational position. So where on the cylinder is the ellipse's highest point? It's kind of difficult to see on this picture, but I think the highest point of this ellipse is somewhere between the 550 nanometers to 600 nanometers, or 55 and 60 in Churchland's units. Now, these three features correspond to three important features of colour. Altitude represents the total energy. It corresponds to brightness and darkness. The higher the ellipse, the brighter the colour is. Tilt corresponds to saturation. This is how vivid, how strong the colour is. So a completely desaturated image would just be black and white. So as you increase the saturation, that strengthens the colours. Rotational position corresponds to hue. Is it red, yellow, green, or what? So this is all represented in this image, which is fairly complicated, I suppose, but you can see that we have the altitude, that's the centre point. The tilt angle is how much it's tilted, and the rotational position is the position of the highest point of the ellipse on the cylinder. and we can associate these three features with features of colour space. Hope that's fairly clear. So here are two metamers for green, a dark, dull green. Now we can roll each of these into a cylinder and work out the ellipse for each one. Churchland calculates the ellipse for the dotted line as having an altitude of 14%, a tilt angle of 17%, and a rotational position of 520 nanometers. For the other line, Churchland calculates the altitude at 13%, a tilt angle of 16%, and a rotational position of 535 nanometers. So they're not exactly the same, but the differences are minor. So it would seem reasonable to class these as the same colour. And if we assume that altitude is brightness, well, we can see that these have a low altitude, so these are quite dark. If tilt angle is saturation, again, these have a low tilt angle, so these would be dull. And if rotational position is hue, we would expect these to be in the middle of the spectrum, so we would expect these to be greenish. So we have a dark, dull, greenish colour, which is exactly how these colours appear. These, as we said, these are two metamers for dark, dull, green. So that seems pretty promising. I've simplified Churchland's account somewhat here, but I hope you get the idea. I think that the basic concept is pretty simple. So let's consider a couple of worries for Churchland's account. First, Ralph Kuhini and C.L. Hardin argue that Churchland's canonical approximations just get the colour wrong for many metamers. Here are the spectral reflectance curves for three metameric greys. The dotted line is grey number 1, the unbroken line here is grey number 2, and the unbroken line in the second image is grey number 3. Now when we work out the ellipses for these greys, it identifies grey 1 as a medium grey colour, grey 2 as a bluish green, and grey 3 as a yellowish red colour. But, as I said, they are all metamers for grey. They all appear the same grey. So it seems that the canonical approximations simply get the expected colour wrong. In these cases, the canonical approximations simply don't match the colour that we perceive. Queenie and Hardin also give some examples of metameric yellows that are incorrectly predicted by the canonical approximations. So this is certainly a problem. Maybe Churchland could respond that the perceptual system isn't perfect. Right? We're able to track canonical approximations, but we can't do it perfectly. There are some cases where the canonical approximation doesn't match the perceived colour. And I suppose that's not too surprising. Perception is very rough around the edges. In most cases, the altitude, tilt angle and rotational position of the ellipse matches the brightness, saturation and hue of the perceived colour. It doesn't do it in all cases, but it's good enough that it does it in most cases. That still counts. In most cases, we get a match. A second objection from Wayne Wright is that Churchland has simply performed a mathematical operation on reflectance curves, and the resulting canonical approximations, as he calls them, do line up fairly neatly, although, as we saw, not perfectly, with colour phenomenology. But what exactly is the physical significance of these canonical approximations? Of these ellipses? What is the physical significance of them? I mean, we could perform all kinds of mathematical operations on spectral reflectance curves to generate sort of new mathematical objects. So to quote Wright, he says, for example, one could redraw the two-dimensional plot of reflectance between 400 and 700 nanometers by taking at each wavelength the cube root of reflectance and multiplying that by the square of the surface's reflectance at the wavelength that is the same absolute distance from 550 nanometers, but in the direction along the x-axis from the wavelength in question. So, just a very complicated operation. Wright continues, the results of any such operations would surely be objective in some sense, but few, if any, would find a home in physical theory. In other words, not just any mathematical construction is going to be interesting from a physical point of view. It's going to be used in physics, in physical theory in general. So, why do canonical approximations matter, but other mathematical operations, such as Wright's operation, don't matter. Why do we take canonical approximations rather than some other mathematical operation to correspond to colour? Well, because canonical approximations end up matching the phenomenology of colour vision. Churchland claims that canonical approximations provide a way of unifying metamers without reference to human colour vision, but the only reason to associate that mathematical operation with colour is that this is the mathematical operation that produces results that match human colour phenomenology. Certainly no scientist cares about canonical approximations. They've just been invented by Churchland to save colour realism. So Churchland claims that canonical approximations are objective properties of the spectral reflectance curves, but that's not really true. I mean, they're a kind of mathematical transformation of the reflectance curve. They're no more or less objective than any other result of a mathematical transformation. Now, if the only reason to talk about canonical approximations is that they provide a way of unifying metamers in a way that corresponds to human perception, then we might wonder, is this really objective after all? I mean, the only reason why we're going with this mathematical operation is that it produces results that correspond to human colour perception. But if you forget about human colour perception and ask, what sort of mathematical operation should we perform on metamers to unify them? Well, there are all sorts of mathematical operations we could perform on these reflectance curves to unify them, and they would be unified in all sorts of different ways. The only reason Churchland goes for this way is because this is the way that agrees with human perception. So, is this objective, or is perhaps Churchland smuggling in a kind of mind dependence? Is he smuggling in a sort of subjective element, rather like the anthropocentric realism of Byrne and Hilbert? So maybe that's something to think about. A third objection is that different surfaces are metamers under different conditions. Indeed, it doesn't really make sense to talk about metamers independently of a specification of the kind of illumination. Two surfaces that match under one illumination will be distinguishable under another. Now, Churchland assumes basically that we're dealing with metamers under daylight during midday. So we're looking at metamers that match under the midday sun. So what unifies metamers are canonical approximations, and we track canonical approximations under daylight. But the question is, why exactly should daylight during midday be taken as standard? Why not tungsten light? Why not pure 537 nanometer light? Why not sunlight at dusk or dawn? In these cases, the metamers will be different, so Churchland's method of unifying metamers will be less effective in these conditions. So those were some problems for Churchland. I think that I'm not sure they quite managed to refute his view. I think that as far as colour realism goes, Churchland has probably got the most plausible approach. So that's something to think about there. Now, in the next video, we will consider whether, assuming the metamer problem can be solved, we will consider whether spectral reflectances are plausible candidates for colours against a few other objections. There are further objections. Metamerism isn't the only one. Metamerism is probably the most serious problem for reductionism, but there are some other very serious problems as well. So even assuming that Churchland's method works, it's not entirely clear that we will actually be able to carry out the reduction. There are other obstacles. But I hope you found that interesting, and I'll see you in the next video. Goodbye.